Hello, everyone, and welcome to the Outspoken Market. Leandro Guerra speaking. Today's class is more than just a probability class, it's the class of understanding the meaning of omega, the space where randomness lives. And that will be very, very clear in the next few minutes. Now, first thing to understand, it's actually what omega represents. In probability theory, everything starts with omega. And why? Because this is what we call the sample space. And by sample space, you can understand the set of all possible outcomes of a given experiment. The easiest and more straightforward example is the coin toss, because you may have heads or tails. This, for a coin, of course, is the set of all possible outcomes. The point is, this is yet a universe where randomness exists for sure, because I don't know what it's going to come after the toss of a coin, if that will land as a head or as a tail. Although if I had all possible information about that launch, eventually would be able to create a model to understand if it's going to land as a head or as a tail. But the biggest point here is not the prediction itself, is given that there is a universe where randomness exists, this set of all possible outcomes, it's omega, and it's given by this mathematical structure over here. So it's the set that it's identified between the keys we have over here of lowercase omegas that are eventually as many as the event that we are going to understand will have. So each one of these lower cases omega are the elements or an elementary outcome, one possible version of that particular reality. In the coin toss, quite straightforward as we have seen. In the case of a temperature measurement, that would be all the real numbers, because I can have negative numbers, I can have positive numbers, I can have zeros if we are speaking about Celsius, for the most common one. Of course, that could go as well in Fahrenheit, whatever. But the biggest point is all the set of the real numbers in this case would be all possible outcomes for the temperature. If we then are going to understand later the temperature set for planet Earth, for example, well, we will not have, for example, the absolute zero, that it's going to be there in kelvins, for example, or even in Celsius. But the biggest point is there will be a subset of all possible outcomes for the temperature that we will explain the temperature or possible to be measuring the temperature of planet Earth. In a stock process, so thinking about stock prices, omega is the set of every, this is the key word, all possible, every possible price path. So it's the core, it's the heart of randomness. And this probability space, to make then omega useful, we have a structure. So not only the set of possible words, but the sigma algebra. There are the measurable subsets of omega. For example, the subset of Earth temperatures, or the temperatures that can be measured on a regular basis in planet Earth, right? So that is the point. Or the price range of an stock over 2024. So there will be these subsets of omega, the questions we can ask. Later, we have the P. The P is the probability measure. So for each event, we are going to have a number between 0 and 1, including 0 or 1. Together, so these three guys over here, they form the mathematical foundation of probability. If we could, in a single picture, in a single page, summarize everything, this is it in terms of foundations of probability. Clear so far? If you have any questions, just drop in the comments. I'm very happy to make another video, another class, everything that is needed to help you. Now, okay, Leandro, we are speaking about randomness. So this is the core, omega, all possible outcomes. We have then the other colleagues, the sigma algebra, the probability measure, and then how this connects to the random variables itself, since we are speaking about foundations of probability. Now, in this particular case, a random variable, so let's denote it as x, it's a function from omega, or in this case we have the uppercase or the capital omega, to the real numbers. Of course, in a word, in an event or a phenomenon that are saying that relates to the real numbers. So each lowercase omega gives a concrete value of x of lowercase omega. If we have this fixed, do you agree with me? We no longer have randomness. We have a deterministic word. Why is that? Well, that guy is fixed. So if x is a function of omega to the real numbers, then if this guy, the lowercase omega, it's one concrete value of x of omega, lowercase in this case, it's a deterministic view. And that is why, this sentence in my view, it's beautiful. That's why randomness, it's simply determinism viewed through uncertainty. If you can isolate that particular fact, you can measure that from the subset of possible events that you are analyzing, it's done. How's that? You may have some expectations over omega, for sure. And we have the expected value that in very, very simple terms can be understood as the mean. Now, in this case, the e of x, or that expected value of a random variable, it's equal to the integral from omega, the capital 1, of x of lowercase omega dp of omega. So in this case, we are averaging all possible words inside omega, weighting them by, remember, what is the lowercase 1? It's a concrete value of x omega, lowercase, weighting them, or weighted by their probabilities under p. This guy, that integral, it's the bridge between what is purely abstract uncertainty to measurable quantities. I know, it might be quite abstract in the beginning, but what is the takeaway that I want you to have? You have no idea about a particular phenomenon. Think about stock prices. There might be, infinite paths that you can have for the S&P 500, for example. So the S&P 500, let's say it's 6,500 now. Then let's say in the next 10 years it will reach 10,000. There are infinite possibilities for the S&P 500 to follow to get to the 10,000. That would be omega. All the possible outcomes. Some of them might be soft paths to there. Some of them will be way more volatile. Some of them will have a huge drawdown before getting a recovery. It doesn't matter. Eventually you will get there, but this can happen in countless ways. So that would be your omega. From here, if you think carefully, then I say, okay, now I understand. If I'm trying to get the point or predicting how and where this is going to be or this is going to go, I would have then to identify the probability of one of the possible paths. Because here in this example, I have set the target 10,000. But I mean, for educational purposes. The point is, I have no idea, nobody has a pale idea what it's going to be the value of the S&P 500 in 10 years time. It could be anything, countless outcomes and ways of getting there. So you would have some assumptions, and from that assumptions, you would have a subset of the possible outcomes that still would have countless outcomes themselves. And from there, you will start elaborating the theory to eventually get to a point of prediction. I mean, randomness is simply beautiful if you start to understand. And the key concept is always the fact that omega is the set of all possible outcomes. And here, there are some misconceptions. Because people may think, well, omega is the set of values of x. No. Omega is the set of underlying scenarios. X maps omega to values. This x is a function from capital omega to the real numbers. That is what x is indeed. We can observe omega. No, you cannot. They're countless. It's all possible outcomes. We only see what we call the realization, the lowercase omega. The capital omega itself cannot be observed. All possible outcomes. Remember that. And omega is fixed by nature. No, it isn't. Omega is chosen by the modeler to describe the experiment's uncertainty. Whenever you have doubts about it, think always about the coin toss or the dice roll. Here, our omega goes a little bit further than just tails and heads. It's from 1 to 6. If I roll a dice, any of these numbers can land. If I roll a dice 1,000 times, I have a lot of possible outcomes around these 1,000 times rolling of a dice. So I must therefore make assumptions to be able to describe the experiment's uncertainty. To never forget, because this class sounds abstract, I know, but it's the foundation of everything. By understanding randomness, you see that in the end of the day, what a model is doing, what a machine learning model is doing, what the large language models are doing. Let's pick up a good example of the large language models. When we say that a large language model has been trained in a billion set of tokens, what it does is, after you write the prompt, it will search throughout that universe what are the points with the highest probability linked to what you have prompted. So there is the capital omega of the large language model. There are the countless combination of words themselves that can be, or tokens themselves that can be put together in order to eventually reply in the right way what you have prompted. The key point is, what is the right way for what you have prompted? It's the realization of that capital omega from the large language model. So it's how you have computed and weighted the probabilities of the tokens that are the lowercase omegas that are possible inside the capital omega space. And of course, in this example, they are not the real numbers, but they are the entire token set for the training of the model. You know what I mean? Is that intelligence? Is that artificial intelligence? Or is just probability? Link it, of course, back to what it's your prompt and what makes sense to have as an answer, but it's all about probabilities. So to remember all the time, capital omega, universe of all possible outcomes. Lowercase omega, it's a single possible word out of that universe of all possible outcomes. Correct? Our other colleague, the sigma algebra, that is part of the key structure that is the mathematical foundation of probability, the sigma alpha. It's a measurable subset of omega. P, it's the probability measure on those subsets. So we link back to here. And capital X, it's a function from omega to the real numbers. Then we close every probability, every expectation, and random model rests on this very simple but wonderful and beautiful idea. Capital omega is the space where randomness lives. Thank you very much. Hope you have enjoyed this class. Much more, it's about to come. Stay tuned, subscribe. See you next time. Bye bye.